Finite difference modeling. Finite difference methods, FDM, are extensively used in seismic modeling and migration. In this lecture, a conventional FDM model was used for modeling, with model input being velocity and density values, and the model produces seismic data. FDM are numerical methods for solving differential equations by approximating them with differential equations, in which finite differences approach derivatives. In seismic wave modeling, FD methods are used to propagate the wave in the subsoil. This method has no immersion limitation and produces all events associated with the wave equation such as multiple reflection, head waves and elastic wave equation, anisotropic effects, and wave conversion data. Therefore, the modeling of the FD wave equations is the ideal way to produce the synthetic seismic data. However, the ultimate goal of migration is to get the image of the real Earth using seismic data, which is difficult to test the accuracy of the migration methods with the desired results. In case of seismic inversion, the entry includes the traces in the output of the structural image. For this purpose, the quantities below must be calculated. Wave propagation angle. Tau two-way travel time. Beta angle of incident from source or receiver. Beta/x geometrical spreading parameter. For each source or receiver, the above quantities must satisfy the equations, where Vx, z, is the velocity and μx z equals tau x tau z minus 1. 1, is the econal equation, x. 3, and 4, are derived from Pusey and Vidal and 5, follows from 3. Plane wave destructors. PWD plane wave destruction filter is derived from the local plane wave model for characterizing the seismic data. This filter operates in the time domain, Tx, such as the time distance, and can be extended to the frequency domain. PWD is constructed using an embedded finite difference scheme for the local plane wave equation as described. For the characterization of several plane waves, it is possible to flow several filters similar to that of the following equation, where Z1, Z2, Zn are the zeros of the polynomial. The Taylor series method, assimilating the coefficients of the expansion of the Taylor series to the zero frequency, gives the expression. For a 3-point centered filter B3, Zt for a 5-point centered filter B5, Zt, the derivation of x, 7, and 8, can be found in FOML. The filter used in the present work is a modified version of filter A, Zt, Zx. This filter avoids the requirement of a polynomial partition. In the case of the 3-point filter, 7, and the two-dimensional filter, 7, there are 6 coefficients consisting of 2 columns, in each column there are 3 coefficients and the second column is an inverse copy of the first one. However, the decomposition algorithm is significantly more expensive than the FD. This algorithm is extended to Song's anisotropic wave propagation in 2013 by involving the eigenfunction rather than rows and columns of the original extrapolation matrix. A. Snapshot of a wave field in a smooth velocity model calculated using the fourth-order finite difference method, and B. The lower rank approximation of the wave field in the same smooth velocity model.